Welcome back to Science with Sleepy, where curiosity drifts like starlight, and tonight's journey stretches across 2 full hours, because the universe never runs out of wonders. Imagine the lights dimmed low, a gentle hum of ambient sound behind my voice, and your favorite blanket pulled close as we drift into one of the most profound questions about the cosmos. Picture this. You step outside on a clear night far from city lights. Above you, thousands of stars twinkle in the darkness. The Milky Way stretches across the sky like a river of light. But what if that light began to fade? What if no new stars were being born? How dark would the night sky become? This isn't just a thought experiment. It's a question about the very nature of our universe, about time on scales so vast they're hard to imagine, and about what happens when the cosmic engine of star formation finally runs out of fuel. Tonight we're going to explore what would happen to the night sky if star formation stopped completely. The idea might sound strange at first. Stars are everywhere, aren't they? Billions of them in our galaxy alone, trillions more in other galaxies. But here's something remarkable. Stars don't last forever. They're born, they live, and they die. And if no new stars are born to replace them, eventually, the lights would go out. As we drift through this 2-hour exploration, we'll discover how stars form, why they shine, and what happens when they die. We'll learn about the different types of stars, and how long they last. We'll explore what would happen if star formation stopped today, and what the night sky would look like in 1 billion years, or 10 billion years, or 1 trillion years from now. The study of star formation is one of the most active areas in modern astronomy. Every year, new telescopes reveal more about how stars are born, and new observations help us understand the cosmic cycle of birth and death. But what happens when that cycle stops? What remains when the last star fades? This question touches on some of the deepest mysteries in science. It connects to the fate of the universe itself, to the nature of time, and to our place in a cosmos that's constantly changing. As we explore this question tonight, we're not just learning about stars, we're learning about the universe's past, present, and future. So settle in, let your breathing slow, and let your mind drift with me into the depths of space and time. We're about to explore what happens when the cosmic lights begin to dim, when star formation ends, and when the universe enters its final dark age. The journey begins now, and it will take us places no human has ever been, to times far in the future, and to questions that have no easy answers. Chapter 1: The Birth of Light. To understand how dark the night would get without star formation, we first need to understand what star formation is and why it matters. Stars are the great light makers of the universe. Without them, the cosmos would be almost completely dark. But how do stars come to be? How does a cloud of gas and dust become a brilliant beacon of light? Star formation begins in the coldest, darkest places in the universe, giant molecular clouds. These are vast regions of space, sometimes hundreds of light-years across, filled with hydrogen gas, helium, and tiny grains of dust. The temperature in these clouds can drop to just 10 Kelvin, which is -263 degrees Celsius. That's colder than liquid nitrogen, colder than the surface of Pluto. At these temperatures, atoms move slowly, and gravity can begin to pull them together. Molecular clouds are among the most massive structures in galaxies. The largest ones can contain enough material to form tens of thousands of stars. The Orion Molecular Cloud Complex, one of the most studied star-forming regions, spans about 1/200 light-years, and contains enough gas to form over 100,000 stars like our Sun. Observations from radio telescopes like ALMA, the Atacama Large Millimeter Array, have revealed the intricate structure of these clouds, showing filaments of gas and dust that stretch for hundreds of light-years. The composition of molecular clouds is mostly hydrogen, about 73% by mass, and helium, about 25%. The remaining 2% consists of heavier elements like carbon, oxygen, nitrogen, and iron, along with tiny dust grains made of silicates and carbon compounds. These dust grains are crucial for star formation because they help the gas cool down by radiating away heat. Without dust, molecular clouds would be too hot to collapse. But these clouds don't collapse easily. They're held up by pressure, by magnetic fields, and by turbulence. For a cloud to collapse and form stars, something needs to trigger it. Sometimes it's the shockwave from a nearby supernova, the explosion of a dying star. Sometimes it's the collision of two molecular clouds. Sometimes it's the gravitational pull of a passing galaxy. Whatever the trigger, once collapse begins, it can't be stopped. The balance between forces is delicate. Thermal pressure from the gas tries to keep the cloud expanded. Magnetic fields, which thread through the cloud, also provide support. And turbulence, the chaotic motion of gas within the cloud, creates pressure that resists collapse. For a cloud to collapse, its mass must be large enough that gravity can overcome all these forces. This is called the Jeans mass, named after the British physicist James Jeans, who first calculated it in 1902. According to research published in the Astrophysical Journal, a typical molecular cloud needs to be about 1,000 to 10,000 times the mass of the Sun to begin collapsing. But once collapse starts, the cloud fragments into smaller pieces, each of which can form one or more stars. This fragmentation process is complex and not fully understood, but observations show that it creates a range of star sizes, from tiny red dwarfs to massive blue giants. The triggers for star formation are varied. Supernova shockwaves are particularly effective because they compress gas rapidly, creating dense regions that can collapse. Studies of star-forming regions show that many young stars are found near the edges of supernova remnants, suggesting that these explosions help trigger new star birth. Collisions between molecular clouds can also compress gas, as can the spiral density waves that move through galaxies, creating regions of higher gas density. As the cloud collapses, it fragments into smaller pieces. Each piece continues to collapse under its own gravity, growing denser and denser. The temperature rises as the gas compresses. At first, the heat can escape, keeping the cloud cool. But as it gets denser, the heat becomes trapped. The temperature climbs from 10 Kelvin to 100 Kelvin, then 1000 Kelvin, then 10,000 Kelvin. This collapse happens in stages. First, the cloud collapses as a whole, taking about 100,000 to 1 million years. During this time, it fragments into clumps, each containing enough mass to form one or more stars. These clumps continue to collapse, taking another 100,000 to 500,000 years. As they collapse, they spin faster, due to conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull in their arms. The spinning creates a disk of material around the central protostar, the object that will become a star. This disk is where planets form, but it also feeds material onto the growing star. Observations from the Hubble Space Telescope and ground-based telescopes have revealed these protoplanetary disks around young stars, showing the early stages of both star and planet formation. As the protostar continues to gather material, its core temperature and pressure increase. The gas becomes so dense that it's no longer transparent. It becomes opaque, trapping heat inside. This is called the adiabatic phase, and it's when the temperature begins to rise rapidly. The protostar glows with infrared light, visible to telescopes but not to human eyes. It's still not a true star yet. That happens when fusion begins. When the temperature reaches about 10 million Kelvin at the center, something amazing happens. Nuclear fusion begins. Hydrogen atoms, which each have one proton, begin to fuse together to form helium, which has 2 protons. This process releases enormous amounts of energy. A single fusion reaction releases more energy than a chemical reaction by a factor of millions. The exact temperature needed for fusion depends on the star's mass. According to calculations by nuclear physicists, stars with about 8% of the Sun's mass need temperatures around 3 million Kelvin to begin fusion, while more massive stars can start fusing at higher temperatures. The Sun's core temperature is about 15 million Kelvin, hot enough to sustain the fusion reactions that power it. This energy is what makes stars shine. It flows outward from the core, pushing against the weight of the star's outer layers. This creates a balance, gravity trying to collapse the star, and fusion energy pushing outward. As long as there's hydrogen to fuse, the star remains stable, shining steadily for millions or billions of years. The process of star formation doesn't happen quickly. It takes hundreds of thousands of years for a cloud to collapse, and millions of years for a star to fully form. But once a star begins fusing hydrogen, it enters what astronomers call the main sequence, the stable phase of its life, where it shines steadily. The exact time it takes for a star to form depends on its mass. Massive stars form faster because their stronger gravity accelerates the collapse. A star 10 times more massive than the Sun might form in just 100,000 years, while a star with half the Sun's mass might take 10 million years. The smallest stars, red dwarfs, can take 100 million years or more to fully form. Once on the main sequence, a star's properties are determined almost entirely by its mass. This relationship was discovered in the early 20th century by astronomers Ejnar Hertzsprung and Henry Norris Russell, who created what's now called the Hertzsprung-Russell diagram. This diagram plots stars by their brightness and color, and it reveals that most stars fall along a diagonal line called the main sequence. Stars spend about 90% of their lives on this line, fusing hydrogen into helium in their cores. The main sequence is where stars are most stable. The balance between gravity and fusion energy keeps them at a constant size and brightness. Our Sun has been on the main sequence for 4.6 billion years, and will remain there for another 5 billion years. During this time it will slowly get brighter, about 1% every 100 million years, as it converts more hydrogen into helium and its core becomes denser and hotter. Not all stars are the same size, and size matters enormously. A star's mass determines almost everything about it: how bright it shines, how long it lives, and how it dies. The smallest stars, called red dwarfs, can be as small as 8% of the Sun's mass. They're dim and cool, glowing with a faint red light. But they're also incredibly long-lived. A red dwarf can shine for trillions of years, far longer than the current age of the universe. The distribution of star masses follows what's called the initial mass function, discovered by astronomer Edwin Salpeter in 1955. This function tells us that for every massive star that forms, many more low-mass stars form. Specifically, for every star 10 times more massive than the Sun, there are about 1,000 stars with the Sun's mass or less. This means that small stars vastly outnumber large stars, even though large stars are much brighter and more visible. The largest stars, called blue supergiants, can be 100 times more massive than the Sun. The most massive star known, R136a1 in the Tarantula Nebula, is about 315 times the Sun's mass. These stars are incredibly bright, shining with a brilliant blue-white light. A star 100 times more massive than the Sun might be 1,000,000 times brighter. But they're also short-lived, burning through their fuel in just a few million years before exploding as supernovae. Between red dwarfs and blue supergiants, there's a whole range of star types. Orange dwarfs like Alpha Centauri b are slightly larger than red dwarfs and live for tens of billions of years. Yellow dwarfs like our Sun live for about 10 billion years. Blue giants, smaller than supergiants but still massive, live for tens of millions of years. Each type has its own characteristics, its own lifetime, and its own way of dying. Our Sun sits in the middle. It's a yellow dwarf, about average in size and brightness. It's been shining for about 4.6 billion years, and it will continue shining for about another 5 billion years before it runs out of hydrogen fuel. When astronomers study other stars, they often compare them to the Sun, using terms like solar mass and solar luminosity to describe their properties. The Sun is our reference point, the star we know best, and the one that makes life on Earth possible. The light from stars travels through space at 300,000 kilometers per second, the speed of light. It takes about 8 minutes for light from the Sun to reach Earth. Light from the nearest star beyond the Sun, Proxima Centauri, takes about 4.2 years to reach us. Light from stars in the center of our galaxy takes about 26,000 years. And light from the most distant galaxies we can see has been traveling for over 13 billion years. When you look up at the night sky, you're seeing light that left those stars at different times. Some of the stars you see might have already died, their light still traveling toward us. Others are just being born, their light just beginning its journey across space. The night sky is like a cosmic time machine, showing us stars at different stages of their lives, all at once. The brightness of a star depends on two things: its size and its temperature. Bigger stars are brighter because they have more surface area to emit light. Hotter stars are brighter because each square meter of their surface emits more light. The relationship is complex, but in general, a star twice as massive might be 10 times brighter, while a star 10 times more massive might be 1,000 times brighter. This relationship follows what's called the mass-luminosity relation, discovered by astronomer Arthur Eddington in the 1920s. For main sequence stars, the luminosity increases roughly as the mass to the 3.5 power. This means that doubling a star's mass increases its brightness by about 11 times. Tripling the mass increases brightness by about 46 times. This is why massive stars are so much brighter than small stars, and why they burn through their fuel so much faster. The temperature of a star's surface determines what color it appears. This follows what's called Wien's law, discovered by physicist Wilhelm Wien in 1893. Hotter objects emit more light at shorter wavelengths. A star with a surface temperature of 30,000 Kelvin emits most of its light in the ultraviolet and blue parts of the spectrum, so it appears blue. A star with a temperature of 3,000 Kelvin emits most of its light in the red and infrared, so it appears red. Our Sun, at 5800 Kelvin, emits most of its light in the yellow-green part of the spectrum, which is why it appears yellow-white. The total amount of light a star emits, its luminosity, is measured in units called solar luminosities. One solar luminosity equals the brightness of our Sun. The brightest stars can be millions of times more luminous than the Sun, while the dimmest red dwarfs might be only 0.0001 times as luminous. This enormous range in brightness is one of the most striking features of stars, and it's all determined by mass and temperature. But brightness also depends on distance. A star that's very bright but very far away might appear dimmer than a star that's less bright but closer. This is why some of the brightest stars in the night sky aren't actually the brightest stars in the galaxy, they just happen to be relatively close to us. The color of a star tells us about its temperature. Hot stars glow blue or white, cool stars glow red or orange. Our Sun, which is medium temperature, glows yellow. This relationship between color and temperature is fundamental to understanding stars. By measuring a star's color, astronomers can determine its temperature, and from its temperature and brightness, they can determine its size and distance. Star formation isn't uniform across the universe. Some regions, like the spiral arms of galaxies, are hotbeds of star formation. Here, molecular clouds are dense and active, constantly giving birth to new stars. Other regions, like the centers of elliptical galaxies, have very little star formation. Most of their stars formed long ago, and few new ones are being born. The rate of star formation in the universe has changed over time. In the early universe, shortly after the Big Bang, star formation was much more active. Galaxies were smaller, gas was more abundant, and conditions were more chaotic. As the universe has aged, star formation has slowed. According to research published by astronomers using data from telescopes like the Hubble Space Telescope and the James Webb Space Telescope, the peak of star formation occurred about 9 to 11 billion years ago. At that time, the universe was forming stars at a rate that was about 30 times higher than it is today. Since then, the rate has declined by about 97%. This means that right now, the universe is forming stars at only about 3% of its peak rate. Dr. Stephen Finkelstein, an astronomer at the University of Texas who studies star formation, explains that this decline is happening because galaxies are running out of gas. As stars form and die, they convert gas into heavier elements, and some gas gets locked up in stellar remnants. Over time, there's simply less gas available to form new stars. Today, in our Milky Way galaxy, about 1 to 2 new stars are born each year. That might not sound like much, but over millions of years, it adds up. The galaxy has been forming stars for about 13 billion years, and in that time, hundreds of billions of stars have been born. Most of them are still shining today, though many of the most massive ones have already died. Some astronomers estimate that no more than 5% additional stars will form over the remaining history of the cosmos. This means that most of the stars that will ever exist have already been born. The universe's star-forming days are mostly behind it, though the process will continue slowly for many billions of years to come. The process of star formation is self-regulating. When stars form, they heat up the surrounding gas, making it harder for more stars to form nearby. When massive stars die in supernovae, they blast gas outward, dispersing molecular clouds and slowing star formation. But they also enrich the gas with heavy elements, which can later help new stars form. It's a complex cycle, with many factors balancing each other. This self-regulation is called feedback, and it's crucial for understanding how galaxies evolve. When young, massive stars form, they emit intense ultraviolet radiation that heats and ionizes the surrounding gas. This creates what's called an HII region, a bubble of hot, ionized hydrogen around the star. The pressure from this hot gas can push against the surrounding molecular cloud, preventing further star formation nearby. This is called radiative feedback, and it limits how efficiently gas can be converted into stars. Observations show that typically only 1 to 5% of the gas in a molecular cloud actually forms stars. The rest is dispersed by feedback processes. This low efficiency is why star formation is a slow process, and why galaxies can continue forming stars for billions of years without running out of gas immediately. Supernova feedback is even more dramatic. When a massive star explodes, it releases as much energy in a few seconds as the Sun will release in its entire 10 billion year lifetime. This energy creates a shock wave that travels through the interstellar medium at thousands of kilometers per second, compressing some gas clouds to trigger new star formation while dispersing others. The supernova also enriches the gas with heavy elements like iron, oxygen and carbon, which were forged in the star's core during its life and during the explosion itself. These heavy elements are crucial for future star formation, because they help gas cool more efficiently. Dust grains, made of heavy elements, can radiate away heat, allowing gas clouds to collapse. Without heavy elements from previous generations of stars, star formation would be much less efficient. This means that the first stars in the universe, which formed from pure hydrogen and helium, were likely very different from stars today. They were probably much more massive, because without heavy elements, gas couldn't cool as efficiently, so only very large clouds could collapse. The balance between these feedback processes determines how quickly galaxies form stars, and how long they can continue doing so. In the early universe, when gas was abundant and feedback was less effective, star formation was rapid. Today, with less gas and more efficient feedback, star formation is slower. This is one reason why the universe's star formation rate has declined so dramatically over time. But what if that cycle stopped? What if, for some reason, star formation came to an end? To understand that, we need to think about what's currently lighting up the night sky, and what would happen if no new stars were born to replace the ones that die. Chapter 2: The Current Night Sky. Right now, as you look up at the night sky, you're seeing light from many different sources. Understanding what you're seeing will help us understand what would disappear if star formation stopped. So let's take a journey through the current night sky, exploring all the sources of light that make it beautiful and bright. The most obvious sources of light are the stars themselves. On a clear, dark night, far from city lights, you can see about 500 to 3,000 stars with the naked eye. But that's just a tiny fraction of what's actually there. The Milky Way galaxy contains between 100 and 400 billion stars. Most are too faint or too far away to see without a telescope. The exact number of stars visible to the naked eye depends on several factors: the darkness of the sky, the sharpness of your vision, and your location on Earth. From the darkest locations on Earth, under perfect conditions, you might see up to 4,000 or 5,000 stars. But from a typical suburban location, you might see only 200 to 500 stars. From a city, you might see only 20 to 50 of the brightest stars. The stars you can see are all relatively close, within about 1,000 light-years of Earth. Beyond that distance, even bright stars become too faint to see without a telescope. The most distant star visible to the naked eye is probably V762 Ceres, in the constellation Cassiopeia, about 16,000 light-years away. But it's only barely visible under perfect conditions. Most naked eye stars are much closer, within a few hundred light-years. The total number of stars in the Milky Way is uncertain, because many are hidden behind dust clouds, or are too dim to detect. Estimates range from 100 billion to 400 billion, with recent studies suggesting the number is closer to 200 billion. The European Space Agency's Gaia mission, which is mapping the positions and motions of over 2 billion stars, is helping refine this estimate. But even Gaia can only see the brightest stars in the most distant parts of the galaxy. The stars you can see are mostly relatively close and relatively bright. The closest star to Earth, Proxima Centauri, is about 4.2 light-years away. It's a red dwarf, too dim to see without a telescope. The brightest star in the night sky, Sirius, is about 8.6 light-years away. It's actually a binary system, two stars orbiting each other, and the brighter one is about 25 times more luminous than the Sun. The stars in the night sky come in different colors, which tells us about their temperatures and ages. Blue stars like Rigel in the constellation Orion are hot and young, often less than 100 million years old. They burn through their fuel quickly and won't last long. Red stars like Betelgeuse, also in Orion, are cooler and older. They're in the later stages of their lives, having expanded into red giants. Rigel is a blue supergiant, about 21 times more massive than the Sun, and 120,000 times brighter. It's only about 8 million years old, a baby compared to the Sun's 4.6 billion years. But it will die much sooner, probably within the next few million years, when it explodes as a supernova. Its blue color comes from its surface temperature of about 12,000 Kelvin, much hotter than the Sun's 5,800 Kelvin. Betelgeuse, on the other hand, is a red supergiant, about 15 to 20 times more massive than the Sun. It's much older than Rigel, probably around 8 to 10 million years old, but it's nearing the end of its life. It has expanded to about 1,000 times the Sun's diameter. If it were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Its red color comes from its cooler surface temperature of about 3,500 Kelvin. Betelgeuse is expected to explode as a supernova within the next 100,000 years, and when it does, it will be visible during the day for weeks. The constellation Orion is particularly interesting because it contains stars at many different stages of life. Rigel and Betelgeuse are both massive stars, but Rigel is young and blue, while Betelgeuse is old and red. The three stars of Orion's belt are all blue giants, similar to Rigel but smaller. And the stars in Orion's sword include the Orion Nebula, a stellar nursery where new stars are being born right now. This makes Orion a perfect example of the stellar life cycle, all visible in one constellation. The Milky Way itself creates a band of light across the sky. This isn't light from a single source, but the combined light of billions of stars, so distant that they blur together into a glowing river. The Milky Way is brightest toward the center of our galaxy, in the direction of the constellation Sagittarius, about 26,000 light-years away. The Milky Way appears as a band because we're inside a flat, disc-shaped galaxy. When we look along the plane of the disk, we see many stars in a line, creating the band. When we look away from the plane, we see fewer stars, so the sky is darker. The band is about 20 to 30 degrees wide, depending on where you look, and it stretches all the way across the sky. The center of the galaxy is particularly bright, because that's where stars are most densely packed. Within the central 1,000 light-years, there are millions of stars packed into a relatively small volume. The density of stars near the center is about 1 million times higher than near the Sun. This makes the galactic center one of the brightest regions in the night sky, though much of its light is hidden by dust clouds that lie between us and the center. The total brightness of the Milky Way is difficult to measure because we're inside it, but estimates suggest it's equivalent to about 20 billion suns. That's the combined light of all the stars in our galaxy. But most of this light comes from a relatively small number of bright, massive stars. The majority of stars in the galaxy are dim red dwarfs that contribute little to the overall brightness. The Milky Way also contains dark lanes, where dust clouds block the light from stars behind them. These create the appearance of rivers of darkness running through the band of light. The most prominent is the Great Rift, a dark band that splits the Milky Way in two, along much of its length. This isn't an absence of stars, but rather dense clouds of dust that absorb starlight, making the stars behind them invisible. But stars aren't the only sources of light in the night sky. There are also nebulae, clouds of gas and dust that glow with their own light. Some nebulae shine because they're being heated by nearby stars. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is a stellar nursery where new stars are being born. The light from these young stars illuminates the surrounding gas, making it glow. Other nebulae are the remains of dead stars. When a massive star explodes as a supernova, it blasts its outer layers into space, creating a glowing cloud called a supernova remnant. The Crab Nebula, the remains of a supernova that exploded in 1054, is still expanding and glowing today, nearly 1,000 years later. Chinese and Arab astronomers recorded this supernova, which was visible during the day for 23 days and remained visible at night for nearly 2 years. Modern observations show that the nebula is expanding at about 1/500 kilometers per second, and it now spans about 11 light-years across. At its center lies a pulsar, a rapidly spinning neutron star that rotates 30 times per second, emitting pulses of radiation that we can detect on Earth. Planetary nebulae are created when smaller stars like our Sun reach the end of their lives. As they expand into red giants and then shed their outer layers, they create beautiful glowing shells of gas. These nebulae are called planetary, not because they have anything to do with planets, but because early astronomers thought they looked like planets through their telescopes. The planets in our solar system also contribute to the night sky's light. Venus, the brightest object in the sky after the Sun and Moon, reflects sunlight so brightly that it can cast shadows. Jupiter and Saturn are also visible to the naked eye, appearing as bright stars that don't twinkle like real stars do. The Moon, of course, is the brightest object in the night sky. It reflects sunlight, and when it's full, it's bright enough to read by. But the Moon's light is just reflected starlight from our Sun. Without the Sun, the Moon would be completely dark. Beyond our galaxy, there are other galaxies, each containing billions of stars. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is visible to the naked eye on dark nights as a faint, fuzzy patch. It's about 2.5 million light-years away, and its light has been traveling for 2.5 million years to reach us. More distant galaxies are too faint to see without telescopes, but they're there, billions of them, each contributing a tiny amount of light to the cosmic background. The Hubble Space Telescope, by pointing at a seemingly empty patch of sky for days, has revealed thousands of galaxies in an area smaller than the Moon. Each of those galaxies contains billions of stars. The most famous of these deep-field images is the Hubble Ultra Deep Field, taken in 2004. By pointing the telescope at a patch of sky in the constellation Fornax for over 11 days, Hubble revealed about 10,000 galaxies in an area that covers only 1/13 of the sky. If you could see this level of detail across the entire sky, you would see about 100 billion galaxies, each containing billions of stars. The James Webb Space Telescope has taken this even further. Its first deep-field image, released in 2022, shows galaxies so distant that their light has been traveling for over 13 billion years, from when the universe was less than 1 billion years old. These early galaxies are smaller and dimmer than modern galaxies, but they're forming stars at a much higher rate, making them visible across cosmic distances. The light from these distant galaxies is incredibly faint. A typical galaxy might emit as much light as 10 billion suns. But from billions of light-years away, it appears as just a tiny smudge. The total light from all distant galaxies creates what's called the extragalactic background light, a faint glow that fills the entire sky. This background is so dim that it's completely invisible to the naked eye, but sensitive instruments can detect it. It represents the combined light from all the stars in all the galaxies that have ever existed, a testament to the universe's long history of star formation. There are also other sources of light that are less obvious. Airglow, a faint light emitted by Earth's atmosphere, adds a subtle glow to the night sky. This is caused by atoms and molecules in the upper atmosphere being excited by solar radiation during the day, and then releasing that energy as light at night. Airglow is always present, even on the darkest nights, and it makes the night sky about 10 times brighter than it would be without an atmosphere. Zodiacal light, sunlight scattered by dust in the inner solar system, creates a faint cone of light along the ecliptic, the path the sun takes across the sky. This dust comes from comets and asteroids, and it forms a disk that extends throughout the inner solar system. Zodiacal light is brightest near the horizon after sunset, or before sunrise, when the sun is just below the horizon, but its light still illuminates the dust. It's about as bright as the Milky Way, making it one of the brighter natural sources of light in the night sky. The Gegenschein, a faint brightening opposite the sun, is another subtle source of light. It's caused by the same interplanetary dust that creates zodiacal light, but viewed from directly opposite the sun. The Gegenschein is much fainter than zodiacal light, and is only visible under the darkest conditions. It appears as a faint oval of light, about 10 degrees across, in the part of the sky directly opposite the sun. There are also other subtle sources of light. The aurora, when present, can make the night sky much brighter, though it's only visible at high latitudes. Meteor trails, when meteors burn up in the atmosphere, create brief flashes of light. And satellites, especially those in low Earth orbit, can reflect sunlight and appear as moving points of light. The International Space Station, for example, can be as bright as Venus when it passes overhead, but the dominant source of light in the night sky is stars. Everything else is secondary. The nebula glow because of stars. The planets shine by reflecting starlight. Even the cosmic microwave background, the afterglow of the Big Bang, is a form of light, though it's not visible to the naked eye. The brightness of the night sky is measured in units called magnitudes. The scale is logarithmic, meaning each step represents a change in brightness by a factor of about 2.5. The brightest stars are around magnitude 1 or 2. The faintest stars visible to the naked eye are around magnitude 6. With binoculars, you can see stars down to about magnitude 9 or 10. With large telescopes, you can see objects down to magnitude 30, or fainter. The total amount of light in the night sky from all stars is surprisingly small. If you could gather all the starlight from the entire night sky and focus it into a single point, it would be about as bright as a single candle seen from a few meters away. That's how faint starlight really is. We see so many stars not because they're bright, but because our eyes are sensitive and the sky is dark. However, this measurement assumes you're in a truly dark location, far from city lights. According to research by the International Dark Sky Association, more than 80% of people on Earth live under light-polluted skies, where the Milky Way is invisible. In urban areas, artificial light can make the night sky 10 to 100 times brighter than natural starlight, dramatically reducing the number of visible stars. A study published in Science in 2023 found that light pollution is increasing by about 9.6% per year globally. This means that a child born in an area where 250 stars are visible might see fewer than 100 stars by their 18th birthday, even if star formation continues. So the darkness of the night sky isn't just about star formation, it's also about how we light our world. The darkness of the night sky itself is a puzzle that has fascinated astronomers for centuries. It's called Olbers' paradox, named after the German astronomer Heinrich Olbers, who asked in 1823, if the universe is infinite and full of stars, why isn't the night sky bright everywhere? The answer involves several factors. First, the universe has a finite age of 13.8 billion years, so light from stars beyond a certain distance hasn't had time to reach us yet. Second, the universe is expanding, which causes light from distant stars to stretch into longer, invisible wavelengths, a phenomenon called redshift. Third, distant stars are simply too faint to see, even with telescopes. However, there's an interesting nuance here. Some astronomers have calculated that if star formation had been constant throughout the universe's history, and if the universe were truly infinite and static, the night sky would indeed be as bright as the surface of the sun. The fact that it's dark tells us something profound about the universe. It's not infinite in the way we might imagine, it's expanding, and it has a beginning. This paradox, first seriously considered by Olbers, helped lay the groundwork for our modern understanding of cosmology. But what if star formation stopped? What would happen to all these sources of light? The answer depends on time. Immediately nothing would change. The stars that are shining now would continue to shine. But over time, as stars die and no new ones are born to replace them, the night sky would gradually darken. The rate of darkening would depend on the types of stars. Massive stars die quickly, in just a few million years. Smaller stars live much longer. Red dwarfs can shine for trillions of years, so the darkening wouldn't be uniform. The brightest, bluest stars would disappear first, leaving behind the dimmer, redder stars. But even those would eventually fade. And as they do, the night sky would become darker and darker, until eventually almost nothing would remain. Chapter 3: The End of Birth. What would cause star formation to stop? This is a question with many possible answers, and understanding them helps us understand what would happen to the night sky. Star formation requires several things: gas, gravity, and the right conditions. If any of these are removed, star formation would cease. One possibility is that the universe simply runs out of gas. Stars form from molecular clouds which are made of hydrogen and helium, the two lightest elements. As stars form and die, they convert some of this gas into heavier elements and blast it into space. But over time, more and more gas gets locked up in stars, white dwarfs, neutron stars, and black holes. Eventually, there might not be enough free gas left to form new stars. This process is already happening, but very slowly. The universe is about 13.8 billion years old, and star formation has been declining for the last 10 billion years. According to research published in the Astrophysical Journal, the current star formation rate is only about 3 to 5% of what it was at its peak. Current estimates suggest that star formation will continue for another 100 billion years or more, gradually slowing as gas becomes scarcer. However, some models predict that star formation could effectively stop much sooner, within 10 to 20 billion years, as galaxies exhaust their gas supplies. But in a hypothetical scenario where star formation stops completely, we can explore what would happen. Interestingly, not all astronomers agree on exactly when star formation will end. Some studies suggest that small, isolated galaxies might continue forming stars for trillions of years, while larger galaxies might stop much sooner. The exact timeline depends on many factors, including how efficiently galaxies can recycle gas from dying stars back into star-forming clouds. Another possibility is that something disrupts the conditions needed for star formation. Molecular clouds need to be cold and dense to collapse. If something heats them up or disperses them, star formation would stop. This could happen if the universe's expansion accelerates enough, or if some cosmic event disrupts the galactic structure. But let's imagine that star formation stops completely, right now, today. What would happen immediately? The answer is, almost nothing, at least not that we would notice. The stars that are shining now would continue to shine. The night sky would look exactly the same tonight, and tomorrow night, and for thousands of years to come. This is because stars have already formed, they're already burning their fuel, already shining. Stopping new star formation doesn't affect the stars that already exist. It's like turning off a factory that makes light bulbs. The light bulbs that are already made and already turned on will continue to shine until they burn out. But over longer timescales, the effects would become noticeable. The first to disappear would be the massive bright stars. These stars burn through their fuel quickly. A star 10 times more massive than the Sun might live only 20 million years. A star 50 times more massive might live just a few million years. These massive stars are also the brightest. They dominate the night sky in regions where they exist. In star-forming regions like the Orion Nebula, the brightest stars are all young, massive stars. If star formation stopped, no new massive stars would be born, and within a few million years, the existing ones would begin to die. The impact would be most noticeable in star-forming regions. The Orion Nebula, for example, contains the Trapezium cluster, a group of 4 massive stars that are among the brightest in the nebula. These stars are only about 1 million years old, and they're responsible for much of the nebula's glow. If star formation stopped, no new trapezium-like clusters would form, and within a few million years, the existing massive stars would begin to die, making these regions much dimmer. When a massive star dies, it does so spectacularly. It explodes as a supernova, briefly outshining entire galaxies. A typical supernova releases as much energy in a few seconds as the Sun will release in its entire 10 billion-year lifetime. For a few weeks or months, it becomes one of the brightest objects in the sky, visible even during the day if it's close enough. The supernova of 1054, which created the Crab Nebula, was visible during the day for 23 days, and remained visible at night for nearly 2 years. But then it fades, leaving behind either a neutron star or a black hole, both of which are dark and invisible. A neutron star is only about 20 kilometers across, but contains more mass than the Sun. It's so dense that a teaspoon of neutron star material would weigh 1 billion tons. Neutron stars can emit radiation, especially if they're pulsars, but this radiation is usually in radio waves or X-rays, not visible light. Black holes emit no light at all, except for the faint glow from matter falling into them, which is rare. So when massive stars die, they take their light with them. The supernova itself is bright, but brief. After it fades, there's nothing left to see. This is why, if star formation stopped, the brightest stars would disappear first, and the night sky would become progressively dimmer. So within a few million years of star formation stopping, the brightest stars would begin to disappear. The night sky would become noticeably dimmer, especially in regions that currently have many young, massive stars. But most stars aren't massive. Most stars are small red dwarfs, which can live for trillions of years. According to surveys of nearby stars conducted by astronomers, red dwarfs make up about 75% of all stars in our galaxy. These stars would continue to shine long after the massive stars are gone, but they're also much dimmer. A typical red dwarf might be 1,000 times dimmer than the Sun, and some of the smallest ones are 10,000 times dimmer. Interestingly, while red dwarfs are the most common type of star, they're also the hardest to see. Most red dwarfs are too faint to be visible to the naked eye, even though they're the closest stars to Earth. Proxima Centauri, the nearest star beyond the Sun, is a red dwarf that's completely invisible without a telescope, even though it's only 4.2 light-years away. So even though red dwarfs would still be shining long after other stars have died, the night sky would be much darker. You might only be able to see a few dozen stars with the naked eye, all of them relatively nearby red dwarfs, glowing with a faint red light. The brilliant blue and white stars that currently dominate the night sky would be gone forever. Medium-sized stars like our Sun would last longer than massive stars, but not as long as red dwarfs. The Sun will shine for about 10 billion years total, and it's already about halfway through its life. So if star formation stopped today, stars like the Sun would continue to shine for about 5 billion more years before they too begin to fade. As stars age, they change. The Sun, for example, will gradually get brighter and hotter as it ages. This happens because as the Sun fuses hydrogen into helium, its core becomes denser and hotter, which increases the rate of fusion. In about 1 billion years, it will be about 10% brighter than it is now. This will make Earth too hot for life as we know it, but the Sun itself will continue to shine. The Sun's brightness increase is slow but steady. Over the next 5 billion years, it will get about 40% brighter. This gradual increase is part of normal stellar evolution for stars like the Sun. Astronomers have observed this process in other stars, and computer models confirm that it's happening to our Sun right now, though the change is too slow for us to notice in a human lifetime. After the Sun runs out of hydrogen fuel in its core, it will expand into a red giant, becoming hundreds of times larger and thousands of times brighter. This happens because the core contracts and heats up, while the outer layers expand and cool. The Sun's surface will extend beyond the orbit of Earth, and its brightness will increase to about 2,000 times its current level. This phase will last for about 1 billion years. During this time, the Sun would be one of the brightest stars in the night sky, visible even during the day. From another planet, it would appear as a brilliant red point of light, dominating the night sky. But then it will shed its outer layers and collapse into a white dwarf, a dense, Earth-sized object that glows faintly with leftover heat. The outer layers will form a planetary nebula, a beautiful shell of glowing gas that will expand and fade over tens of thousands of years. The white dwarf at the center will initially be very hot, about 100,000 Kelvin, and will glow with a brilliant white light, but it will cool over time, becoming dimmer and redder, until eventually it becomes a black dwarf, completely dark. White dwarfs are interesting because they don't produce new energy through fusion, they just glow with the heat they retained when they formed. Over time they cool down and fade. A white dwarf that's 10 billion years old might still glow faintly, but one that's 100 billion years old would be much dimmer. After trillions of years, white dwarfs would cool completely and become black dwarfs, dark objects that emit no light at all. So the timeline of darkening would be gradual. Within a few million years, the brightest stars would be gone. Within a few billion years, medium-sized stars like the Sun would begin to fade. Within tens of billions of years, most stars would be gone, leaving only the longest-lived red dwarfs and the cooling white dwarfs. But even red dwarfs don't last forever. They shine by fusing hydrogen, and eventually, they too will run out of fuel. The smallest red dwarfs, which are the most efficient at using their fuel, might shine for 10 trillion years or more. But eventually, even they would fade. After all the stars are gone, what would remain? The answer is, not much, at least in terms of visible light. White dwarfs would continue to glow faintly for trillions of years, but they would be very dim. Neutron stars and black holes would be completely dark. The universe would enter what astronomers call the degenerate era, a time when the only sources of light are the cooling remnants of dead stars. But there would still be some light, just not from stars. The cosmic microwave background, the afterglow of the Big Bang, would still be there, though it would be even colder and fainter than it is now. And there might be other sources of light that we haven't discovered yet. The key point is that the darkening would be gradual. It wouldn't happen overnight, or even over a human lifetime. It would take millions, billions, or trillions of years. But it would be inevitable. Without new star formation, every star that exists today will eventually die, and no new ones will be born to replace them. Chapter 4: The Gradual Darkening. Let's imagine we could fast forward through time and watch what happens to the night sky as star formation stops and existing stars begin to die. The darkening wouldn't be sudden, it would be a slow, gradual process, happening over timescales so vast they're hard to imagine. But we can break it down into stages, each marked by different types of stars fading away. The first stage would begin immediately, though we wouldn't notice it for a long time. Within the first million years, the most massive stars would begin to die. These are the O-type and B-type stars, the hot, blue, brilliant stars that dominate young star clusters. They burn through their fuel in just a few million years, and when they die, they explode as supernovae. O-type stars are the most massive and hottest, with surface temperatures above 30,000 Kelvin. They're incredibly rare. Only about 1 in 3 million stars is an O-type star. But they're so bright that they dominate the light output of their host galaxies. A single O-type star can be 1 million times brighter than the Sun. But they live for only 3 to 6 million years before exploding as supernovae. B-type stars are slightly less massive, with surface temperatures between 10,000 and 30,000 Kelvin. They're more common than O-type stars but still rare, making up about 0.1% of all stars. They live for 10 to 100 million years, still very short compared to the Sun's 10 billion years. When they die, the most massive B-type stars explode as supernovae, while the less massive ones become white dwarfs. In star clusters, these massive stars create what's called the main sequence turnoff, the point on the Hertzsprung-Russell diagram, where stars have just left the main sequence. By studying this turnoff point, astronomers can determine the age of a cluster. In a cluster that's 10 million years old, O-type stars are just beginning to die. In a cluster that's 100 million years old, all O-type stars are gone, and B-type stars are beginning to die. This is how we know that if star formation stopped, the brightest stars would disappear first. A supernova is one of the most spectacular events in the universe. For a brief moment, a single star can outshine an entire galaxy. If a supernova occurred in our galaxy, it would be visible during the day for weeks or months, but then it would fade, leaving behind a neutron star or black hole, both completely dark. So within a few million years, the brightest blue stars would be gone. The night sky would lose its hottest, most brilliant points of light. Star-forming regions like the Orion Nebula would still glow from the gas being heated by remaining stars, but the brightest stars themselves would be gone. The next stage would take longer, tens of millions of years. The medium-mass stars, those between about 2 and 8 times the Sun's mass, would begin to reach the end of their lives. These stars live for hundreds of millions to a few billion years. They don't explode as supernovae, but instead expand into red giants and then shed their outer layers, becoming white dwarfs. During their red giant phase, these stars become much brighter, sometimes thousands of times brighter than they were on the main sequence. A star like the Sun, which is about 1 solar luminosity on the main sequence, might reach 2,000 solar luminosities as a red giant. This happens because the star expands to hundreds of times its original size, increasing its surface area, while the core becomes much hotter, increasing the energy output. So for a while, the night sky might actually get brighter as more stars enter their red giant phase. This would be most noticeable in older star clusters and in the central regions of galaxies, where many stars are reaching the end of their main sequence lifetimes at the same time. The combined light from hundreds or thousands of red giants could make these regions significantly brighter than they are today. But this would be temporary. After a billion years or so, they would all have become white dwarfs, which are much dimmer. The transition from red giant to white dwarf happens relatively quickly, in just a few tens of thousands of years. The star sheds its outer layers, creating a planetary nebula, and the core collapses into a white dwarf. The planetary nebula glows brightly for about 10,000 to 20,000 years, then fades as it expands and cools. The white dwarf remains, but it's much dimmer than the red giant was. This means there would be a brief period, perhaps a few 100 million years, when the night sky would be brighter than it is today, due to the large number of red giants. But this would be followed by a much longer period of gradual dimming, as white dwarfs cool and fade, and as fewer and fewer stars remain on the main sequence. White dwarfs are fascinating objects. They're about the size of Earth but contain as much mass as the Sun. They're incredibly dense. A teaspoon of white dwarf material would weigh as much as an elephant. They glow with leftover heat from their formation, but they don't produce new energy. Over time, they cool down and fade. A newly formed white dwarf might have a surface temperature of 100,000 Kelvin and glow with a brilliant white light. But over billions of years, it cools. According to calculations by astrophysicists who study stellar evolution, a white dwarf cools following a specific pattern. After 10 billion years, it might be down to 4,000 Kelvin, glowing with a dim red light. After 100 billion years, it might be down to 1,000 Kelvin, barely visible in the infrared spectrum. Research published in the monthly notices of the Royal Astronomical Society by Dr. Pierre-Emmanuel Tremblay and his colleagues has shown that white dwarfs cool more slowly than we once thought. Their study of thousands of white dwarfs revealed that some processes, like the crystallization of material inside the white dwarf, can actually slow down the cooling process. This means white dwarfs might remain visible longer than previous estimates suggested. After trillions of years, white dwarfs would cool completely and become black dwarfs, dark objects that emit no light at all. However, no black dwarfs exist yet in the universe, because the universe isn't old enough. The first black dwarfs won't form for another 10 to 15 trillion years, long after the last stars have died. The Sun will become a white dwarf in about 7.5 billion years. If star formation stopped today, the Sun would continue to shine normally for about 5 billion more years, then expand into a red giant for about a billion years, and finally collapse into a white dwarf. That white dwarf would then glow faintly for trillions of years before cooling completely. But most stars in the galaxy are smaller than the Sun. Red dwarfs, which make up about 75% of all stars, can live for trillions of years. The smallest red dwarfs, those with about 8% of the Sun's mass, might shine for 10 trillion years or more. According to stellar evolution models developed by astronomers, a red dwarf with 8% of the Sun's mass would fuse hydrogen so slowly that it could maintain stable fusion for up to 12 trillion years. That's about 900 times longer than the current age of the universe. Dr. Gregory Laughlin, an astrophysicist at Yale University who studies the long-term future of stars, has calculated that the very smallest red dwarfs might even last for 20 trillion years or more. These tiny stars are incredibly efficient at using their fuel, converting almost all of their hydrogen into helium over their extremely long lifetimes. So even after the Sun and other medium-mass stars are gone, the night sky would still have many dim red points of light. These would be the longest-lived stars in the universe, the last beacons of light in an otherwise darkening cosmos. These red dwarfs are much dimmer than the Sun. The faintest ones visible to the naked eye are about 1,000 times dimmer than the Sun, so the night sky would be much darker, but not completely dark. You might still be able to see some stars, though far fewer than today. Over tens of billions of years, even the red dwarfs would begin to fade. As they run out of hydrogen fuel, they would expand slightly and get a bit brighter, but then they would cool and dim. The smallest red dwarfs would be the last to fade, but eventually, even they would die. After all the stars are gone, what would remain? White dwarfs would continue to glow faintly for trillions of years, but they would be very dim, and most would be too faint to see with the naked eye. The night sky would be almost completely dark, with only the faintest glimmers from cooling stellar remnants. But there would still be some light, just not from stars. The cosmic microwave background, the afterglow of the Big Bang, would still be there. Right now, it has a temperature of about 2.7 Kelvin, which corresponds to microwave radiation, not visible light. But as the universe expands and cools, this background would become even colder and fainter. There might also be other sources of light. Brown dwarfs, objects too small to be stars but larger than planets, might continue to glow faintly. Some brown dwarfs can maintain fusion of deuterium, a heavy form of hydrogen, for billions of years. But they're very dim, and most would be too faint to see. Accretion disks around black holes might also produce light. When matter falls into a black hole, it heats up and glows before disappearing. But this would be rare and localized. Most black holes would be completely dark, with no matter falling into them. The timeline of darkening depends on the types of stars. In regions with many massive stars, like spiral arms, the darkening would happen quickly, within millions of years. In regions with mostly small stars, like the halos of galaxies, the darkening would happen much more slowly, over trillions of years. But the overall trend would be clear. The night sky would gradually become darker and darker. The brightest stars would disappear first, then the medium brightness stars, then the dim stars. Eventually, only the faintest glimmers from stellar remnants would remain. This darkening would happen on timescales far longer than human history. We wouldn't notice it in our lifetimes, or even over thousands of years. But over millions and billions of years, the change would be dramatic. The night sky would transform from a brilliant tapestry of stars to an almost empty darkness, with only the faintest points of light remaining. Chapter 5: The Far Future. Let's jump far into the future, to a time when star formation has been stopped for billions of years, and most stars have died. What would the night sky look like then? The answer depends on exactly how far in the future we're looking, but we can explore different scenarios. In 1 billion years, if star formation stopped today, the night sky would still look relatively familiar. Most stars would still be shining. The sun would be about 10% brighter than it is now, but it would still be recognizable. The brightest blue stars would be gone, but red and orange stars would still be visible. The Milky Way would still be a band of light across the sky, though it might be slightly dimmer. The changes would be subtle at first. You might notice that some of the brightest stars in familiar constellations are gone. In Orion, Rigel would be gone, having exploded as a supernova. Betelgeuse might also be gone, or it might be in its final stages before exploding. The constellation would look different, but it would still be recognizable. Star-forming regions like the Orion Nebula would be much dimmer. Without new massive stars being born, the gas clouds would no longer be heated and ionized, so they wouldn't glow as brightly. The nebula would still be there, but it would appear as a dark cloud rather than a glowing region. This would make the night sky appear less colorful, as many of the bright blue and white regions would be gone. The overall brightness of the Milky Way would decrease by perhaps 10 to 20% as the brightest stars disappear. But this would be gradual, happening over millions of years, so it wouldn't be noticeable in a human lifetime. The band of light would still be there, still beautiful, but slightly dimmer than it is today. The main difference would be in star-forming regions. Places like the Orion Nebula, which currently glow with the light of young, massive stars, would be much dimmer. The gas would still be there, but without new stars being born, it wouldn't be heated and wouldn't glow as brightly. In 10 billion years, the changes would be more dramatic. The Sun would have expanded into a red giant, and then collapsed into a white dwarf. It would be much dimmer, glowing with a faint white or blue light, perhaps 1,000 times dimmer than it is today. Most medium-mass stars would also have become white dwarfs. The night sky would be dominated by red dwarfs, the small, dim stars that live the longest. By this time, the Sun would be a white dwarf, about the size of Earth but containing the mass of the Sun. It would have a surface temperature of about 5,000 to 10,000 Kelvin, glowing with a white or blue-white light. But it would be much dimmer than the current Sun, perhaps only 0.1% as bright. From another planet it would appear as a very faint star, barely visible to the naked eye. The night sky would look very different. Most of the bright stars we know today would be gone. Sirius, the brightest star in the current night sky, would be a white dwarf. Vega, Altair and other bright stars would also be white dwarfs. The sky would be dominated by red dwarfs, which are much dimmer. You might only be able to see a few hundred stars with the naked eye, compared to the 500 to 3,000 visible today. The Milky Way would be much dimmer, perhaps 50 to 70% dimmer than it is today. The spiral arms, which are currently bright with young stars, would be dark. Only the older stellar populations would remain, creating a dimmer, more uniform glow. The galaxy would still be visible as a band of light, but it would be much less impressive than it is today. The Milky Way would be much dimmer. Without new stars being born, and with many stars having died, the combined light would be significantly less. The spiral arms, which are currently bright with young stars, would be dark. Only the older stellar populations would remain. In 100 billion years, the changes would be even more dramatic. Most red dwarfs would still be shining, but many white dwarfs would have cooled significantly. They would glow with a dim red light, barely visible. The night sky would be much darker, with only the faintest stars visible. The cosmic microwave background would also have cooled. Right now it has a temperature of 2.7 Kelvin, which was precisely measured by the Planck satellite mission in 2013. This temperature corresponds to microwave radiation, with a wavelength of about 1.9 millimeters, which is not visible to the human eye. In 100 billion years, Due to the expansion of the universe, calculations by cosmologists suggest it might be down to 0.1 Kelvin or less. The cosmic microwave background cools as the universe expands, because the expansion stretches the wavelengths of the radiation, making it cooler. It would still be there, but it would be even fainter and colder, shifting further into the radio part of the spectrum. Dr. Lawrence Krauss, a theoretical physicist who has written extensively about the far future of the universe, notes that the cosmic microwave background is one of the few sources of light that will remain long after all stars have died. But it won't be visible light, it will be in the radio spectrum, detectable only with specialized instruments, not with human eyes. In 1 trillion years, we would be in what astronomers call the degenerate era. Most stars would be gone. Only the smallest, longest-lived red dwarfs would still be shining, and they would be very dim. White dwarfs would have cooled to a few hundred Kelvin, glowing with a faint infrared light that's not visible to the human eye. The term degenerate era comes from the physics of degenerate matter, the state of matter in white dwarfs and neutron stars, where electrons are packed so tightly that quantum mechanical effects become important. During this era, the universe would be dominated by these degenerate objects, along with the few remaining red dwarfs. The night sky would be almost completely dark. You might be able to see a few dim red points of light from the remaining red dwarfs, but they would be very faint. Most would be too dim to see with the naked eye, even if they were relatively close. The brightest red dwarfs might still be visible, but they would appear as very faint red stars, barely distinguishable from the background. The Milky Way would be barely visible, just a faint smudge of light from billions of dim stellar remnants. The band of light that currently stretches across the sky would be gone, replaced by a uniform, very dim glow. Without telescopes, you might not even notice it. The galaxy would still exist, still contain billions of objects, but they would all be dark or nearly dark. The cosmic microwave background would have cooled to about 0.01 Kelvin, far below what it is today. It would still be there, still detectable with sensitive instruments, but it would be completely invisible to human eyes. The universe would be entering its final, dark phase, a time when almost all sources of visible light have faded away. In 10 trillion years, even the longest-lived red dwarfs would begin to fade. As they run out of hydrogen fuel, they would cool and dim. The night sky would be almost completely black, with only the faintest glimmers from cooling white dwarfs and brown dwarfs. After 100 trillion years, the universe would enter what some astronomers call the black dwarf era. All stars would be gone. White dwarfs would have cooled completely and become black dwarfs, dark objects that emit no light. The night sky would be almost completely dark, with only the cosmic microwave background, and perhaps a few other faint sources of light. The black dwarf era would mark the end of the stellar age of the universe. No stars would remain, no fusion would be occurring anywhere. The universe would be filled with dark objects, black dwarfs, neutron stars and black holes. These objects would continue to exist, but they would emit no light, making them invisible. The cosmic microwave background would have cooled to about 0.001 Kelvin, so cold that it would be barely detectable, even with the most sensitive instruments. It would still be there, a remnant of the Big Bang, but it would be so faint and so cold that it would be essentially undetectable. There might still be some sources of light, but they would be rare and faint. Accretion disks around black holes could still produce light if matter falls into them, but by this time, most black holes would be isolated, with no matter nearby. Brown dwarfs, objects too small to be stars, might still glow faintly with residual heat, but they would be very dim and very rare. The night sky would be almost completely black. Without telescopes or other instruments, you would see almost nothing. The universe would have entered its final dark age, a time when light is the exception rather than the rule. This would be the end of the cosmic story of starlight, the final chapter in the universe's long history of creating and destroying stars. But even in this dark future, there might still be some light. Accretion disks around black holes could still produce light if matter falls into them. But this would be rare. Most black holes would be isolated, with no matter nearby to fall in. The expansion of the universe would also affect what we can see. As space expands, distant objects move away from us faster and faster. This is due to dark energy, a mysterious force that's causing the universe's expansion to accelerate. According to measurements from the Hubble Space Telescope and other observatories, dark energy makes up about 68% of the universe's total energy. Eventually, objects would be moving away faster than the speed of light, meaning their light would never reach us. This doesn't violate the laws of physics because it's space itself that's expanding, not the objects moving through space. The observable universe would shrink, and we would see fewer and fewer objects. Dr. Katie Mack, an astrophysicist and author who studies cosmology, explains that in about 100 billion years, all galaxies beyond our local group will have moved beyond our cosmic horizon. We won't be able to see them anymore, not because they've disappeared, but because their light can no longer reach us due to the expansion of space. This would make the universe appear much smaller and darker, even if stars were still shining in those distant galaxies. But this is far in the future, trillions of years from now. For most of the universe's history, even without new star formation, there would still be stars shining. The darkening would be gradual, happening over timescales far longer than the current age of the universe. The key point is that the universe wouldn't go dark immediately. It would take trillions of years for all stars to die. But eventually, without new star formation, the lights would go out. The night sky would become almost completely dark, with only the faintest remnants of the stellar era remaining. This future might seem bleak, but it's also fascinating. It shows us the true scale of cosmic time, and helps us understand the importance of star formation. Without it, the universe would eventually become a dark, cold place. But with it, new stars are constantly being born, ensuring that the cosmic lights never fully go out. Chapter 6: The Cosmic Perspective. As we near the end of our 2-hour journey, let's step back and consider what all of this means. The question of how dark the night would get without star formation isn't just about astronomy. It's about time, about change, and about our place in a universe that's constantly evolving. Star formation is one of the most important processes in the universe. It's how matter organizes itself into structures that can shine, that can create the light we see. Without star formation, the universe would be a very different place. It would be darker, colder, and far less interesting. Stars are the universe's way of converting matter into light. Through fusion, they transform hydrogen and helium into heavier elements, releasing energy in the process. This energy powers the light we see, heats planets, and makes life possible. Without stars, the universe would be a dark, cold place, filled with gas and dust, but no light, no heat, no structure. But star formation is also temporary. It won't last forever. The universe has a finite amount of gas, and eventually, it will all be locked up in stellar remnants. When that happens, star formation will stop, and the universe will enter its final, dark age. The amount of gas available for star formation is decreasing over time. As stars form and die, They convert gas into heavier elements, and lock some of it up in stellar remnants. Some gas is also lost to intergalactic space, where it's too diffuse to form stars. Current estimates suggest that only about 5% more stars will form over the remaining history of the universe. This means that the era of active star formation is mostly behind us, and the universe is gradually transitioning to a darker, quieter phase. This transition is happening slowly, over billions of years, so we won't notice it in our lifetimes, but it's happening nonetheless, and it's one of the most profound changes the universe will ever undergo. The cosmic lights are gradually dimming, and eventually they will go out completely. This might sound depressing, but it's also a reminder of how special this moment is. We live in a time when stars are still being born, when the universe is still active and vibrant. We can look up at the night sky and see thousands of stars, each one a point of light in the darkness. The night sky we see today is the result of 13.8 billion years of star formation. Every star we see was born from a cloud of gas and dust, and everyone will eventually die. But new stars are constantly being born to replace them, ensuring that the cosmic lights continue to shine. If star formation stopped today, we wouldn't notice immediately. The stars that are shining now would continue to shine for millions, billions, or trillions of years. But eventually, they would all fade, and the night sky would become almost completely dark. The timeline of this darkening would be gradual. Within a few million years, the brightest stars would be gone. Within a few billion years, medium-mass stars like the Sun would begin to fade. Within tens of billions of years, most stars would be gone. Within trillions of years, even the longest-lived red dwarfs would fade, leaving only the faintest glimmers from stellar remnants. But this is all hypothetical. In reality, star formation is still happening. New stars are being born all the time, in our galaxy and in galaxies across the universe. The process might be slowing down, but it hasn't stopped, and it won't stop for a very long time. Recent observations from the James Webb Space Telescope, launched in 2021, have actually revealed that star formation in the early universe was even more active than we previously thought. The telescope has detected galaxies forming stars when the universe was only a few 100 million years old, showing that the cosmic engine of Starbirth has been running for almost the entire history of the cosmos. However, astronomers have also confirmed that star formation is declining. A comprehensive study published in Nature in 2023, using data from multiple telescopes, found that the universe's star formation rate has decreased by about 97% since its peak. The study's lead author, Dr. Casey Popovich of Texas A&M University, notes that while star formation continues, we're living in what might be called the twilight years of cosmic starbirth, still active but past its prime. The study of star formation helps us understand not just the present, but also the past and future of the universe. By studying how stars form today, we can understand how they formed in the past, and how the universe has evolved over time. And by understanding the processes that drive star formation, we can predict how it will change in the future. The night sky is a window into the universe's history. When we look at distant galaxies, we're seeing them as they were millions or billions of years ago, when their light began its journey to us. We're seeing a universe that's constantly changing, where stars are born and die, where galaxies evolve, and where new structures are constantly forming. This time travel aspect of astronomy is one of its most fascinating features. When we look at the Andromeda Galaxy, 2.5 million light-years away, we're seeing it as it was 2.5 million years ago. When we look at the most distant galaxies, we're seeing them as they were over 13 billion years ago, when the universe was young. This allows us to study the universe's history directly by looking at objects at different distances and therefore different times. The James Webb Space Telescope has taken this even further, allowing us to see galaxies that formed when the universe was only a few 100 million years old. These early galaxies are different from modern galaxies. They're smaller, more chaotic, and forming stars at a much higher rate. By studying them, we can understand how galaxies evolved over time, and how star formation has changed throughout the universe's history. This historical perspective helps us understand what would happen if star formation stopped. We can see what the universe was like when star formation was more active, and we can project forward to what it might be like when star formation ends. The night sky is not just a beautiful sight, it's a record of cosmic history, a story written in light across billions of years. The question of how dark the night would get without star formation is ultimately a question about time and change. It reminds us that the universe is not static, that everything is in motion, and that the present moment is just one frame in a cosmic movie that's been playing for 13.8 billion years and will continue for trillions more. But it also reminds us of the beauty and wonder of the night sky as it is now. Every star we see is a reminder of the cosmic processes that created it, and of the vast timescales over which the universe operates. The night sky is not just beautiful, it's a testament to the universe's ability to create light from darkness, order from chaos, and beauty from the simplest of ingredients. As we think about the future of the universe, we're also thinking about our place in it. We live on a planet orbiting a star, in a galaxy full of stars, in a universe full of galaxies. We're part of this cosmic story, witnesses to a universe that's still young and active, still forming stars and creating light. The night sky we see tonight is the result of billions of years of cosmic evolution. It's a gift, a reminder of the universe's beauty and complexity. And as long as star formation continues, new stars will be born, ensuring that future generations will also be able to look up and see the wonder of a star-filled sky. And now, as our 2-hour journey comes to a close, let's return to where we began, the question of how dark the night would get without star formation. We've explored how stars are born, what lights up the current night sky, what would happen if star formation stopped, and how the universe would gradually darken over time. The answer is complex. Immediately, nothing would change. The stars that are shining now would continue to shine. But over millions, billions, and trillions of years, the night sky would gradually become darker and darker. The brightest stars would disappear first, then the medium brightness stars, then the dim stars. Eventually, only the faintest glimmers from stellar remnants would remain. But this is all hypothetical. In reality, star formation is still happening. New stars are being born all the time, ensuring that the cosmic lights continue to shine. The universe is still young and active, still full of the processes that create light and beauty. As you drift towards sleep, remember that the stars you see tonight are the result of billions of years of cosmic evolution. Each one is a point of light in the darkness, a reminder of the universe's ability to create beauty from the simplest of ingredients. And as long as star formation continues, new stars will be born, ensuring that the night sky remains a source of wonder and inspiration. The stars we see tonight represent just a moment in the universe's long history. Some are young, just beginning their lives, others are old, nearing the end. But all of them are part of the same cosmic story, the same cycle of birth and death that has been playing out for 13.8 billion years. And this story will continue for trillions of years to come, even as star formation gradually slows and eventually stops. The question of how dark the night would get without star formation is ultimately a question about time and change. It reminds us that the universe is not static, that everything is in motion, and that the present moment is just one frame in a cosmic movie that's been playing for billions of years and will continue for trillions more. But it also reminds us of how special this moment is, how beautiful the night sky is right now, and how fortunate we are to live in a time when stars are still being born. So as you rest, let your mind drift with the stars. Imagine the vast clouds of gas and dust collapsing to form new stars. Picture the light from those stars traveling across space and time to reach your eyes. And remember that you're part of this cosmic story, a witness to a universe that's still young and full of wonder. The night sky is a gift, a reminder of the universe's beauty and complexity, and a testament to the processes that continue to shape the cosmos today. The question of how dark the night would get without star formation is ultimately a question about time, change, and the universe's future. But it's also a reminder of how special this moment is, how beautiful the night sky is right now, and how fortunate we are to live in a time when stars are still being born. So as you rest, let your mind drift with the stars. Imagine the vast clouds of gas and dust collapsing to form new stars. Picture the light from those stars traveling across space and time to reach your eyes. And remember that you're part of this cosmic story, a witness to a universe that's still young and full of wonder. Thank you for joining me on this 2-hour exploration of star formation and the night sky. If these calm, curious journeys help you unwind or spark your imagination, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. The journey we've taken tonight is just the beginning. As telescopes become more powerful, and as our understanding deepens, we'll discover more about how stars form, how they live, and how they die. Each new observation, each new calculation, each new discovery adds another piece to the puzzle. Star formation is teaching us that the universe is more complex, more beautiful, and more wonderful than we ever imagined. The James Webb Space Telescope, launched in 2021, is already revolutionizing our understanding of star formation. It can see through dust clouds that block visible light, revealing stellar nurseries that were previously hidden. It can detect the faint glow of the first stars that formed in the universe, helping us understand how star formation began. And it can study the composition of young stars and their surrounding disks, teaching us about the conditions that lead to planet formation. Future telescopes, like the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, will push these observations even further. They'll be able to see individual stars in distant galaxies, measure the rate of star formation across cosmic time, and study the detailed physics of how stars are born. Each new instrument brings new capabilities, new discoveries, and new questions to explore. But even as we learn more, the fundamental question remains: what happens when star formation stops? The answer is complex, involving timescales so vast they're hard to imagine, processes so slow they're imperceptible, and changes so gradual they span billions of years. But understanding this question helps us understand the universe itself, its past, its present, and its future. As you drift towards sleep, think about those stars out there in the darkness. Some are just being born, their light just beginning its journey across space. Others are in the prime of their lives, shining steadily for billions of years. Still others are nearing the end, preparing to fade away. Each one is unique, each one has its own story, and each one represents a moment in the cosmic cycle of birth and death. The star formation process is happening right now, all around us. In the Orion Nebula, new stars are being born as we speak. In distant galaxies, stellar nurseries are creating new generations of stars. And in our own galaxy, About 1 to 2 new stars are born each year, adding to the cosmic light. This process has been happening for 13.8 billion years, and it will continue for billions more, gradually slowing but never completely stopping. At least not for a very long time. But eventually the cosmic lights will begin to dim. The brightest stars will die first, then the medium brightness stars, then the dim stars. White dwarfs will cool and fade, red dwarfs will exhaust their fuel, and the universe will enter its final, dark age. This won't happen in our lifetimes, or even in the lifetime of our species, but it will happen. The question is not if, but when. Yet even in this dark future, there will still be light, just not from stars. The cosmic microwave background will still be there, a faint remnant of the Big Bang. Accretion disks around black holes might still glow, if matter falls into them, and there might be other sources of light that we haven't discovered yet. The universe will be dark, but not completely black. There will always be some light, some remnant of the cosmic fire that has burned for billions of years. The question of whether the night sky would go dark without star formation might seem like a distant, abstract question. But it's grounded in real science, in real processes that are happening right now, all around us. The stars we see tonight are proof that star formation is still active, that the universe is still creating light, and that the cosmic story is still being written. As we've explored tonight, the darkening would be gradual, happening over timescales far longer than human history. We wouldn't notice it in our lifetimes, or even over thousands of years, but over millions and billions of years, the change would be dramatic. The night sky would transform from a brilliant tapestry of stars to an almost empty darkness. But this is all hypothetical. In reality, star formation continues. New stars are being born, ensuring that the cosmic lights never fully go out. The universe is still young, still active, and still full of the processes that create light and beauty. The night sky we see tonight is a gift, a reminder of the universe's beauty and complexity. It's a testament to billions of years of cosmic evolution, and to the processes that continue to shape the universe today. As long as star formation continues, new stars will be born, and the night sky will remain a source of wonder and inspiration. Now, let the stars dim behind your thoughts. We've traveled through time and space, explored the birth and death of stars, and pondered the future of the universe itself. The cosmos is vast, and full of mysteries. And you, right here, right now, are part of it all. The night sky we see tonight is the result of billions of years of cosmic evolution. Every star, every nebula, every galaxy, represents a moment in this long story. And as long as star formation continues, new chapters will be written, new stars will be born, and the cosmic lights will continue to shine. The question of how dark the night would get without star formation is ultimately a reminder of how special this moment is. We live in a time when stars are still being born, when the universe is still active and vibrant, when the cosmic lights are still bright. This won't last forever, but it's happening now, and we're here to witness it. So as you rest, let your mind drift with the stars. Imagine the vast clouds of gas and dust collapsing to form new stars. Picture the light from those stars traveling across space and time. And remember that you're part of this cosmic story, a witness to a universe that's still young and full of wonder. The journey doesn't end here. It continues every time we look up at the stars, every time we wonder about the universe, and every time we remember that we're part of something vast and mysterious. The night sky is a gift, a reminder of the universe's beauty, and a testament to the processes that continue to shape the cosmos. Rest well, and may your dreams drift among the stars. The universe is vast, and full of wonders. And the night sky, with all its stars and galaxies, is a reminder that we're part of something much larger than ourselves. Good night, and may the stars guide your dreams.